So, we continue with our discussion on the iron ore reduction, where we have not assumed any step to be rate limiting, and indeed we try to categorize, as I presented in the last lecture, through 3 steps, and the treatment of the 3 steps when they are none of them could be regarded as a slow kinetic step or fast kinetic step, how it is going to be done. So, we have a boundary layer transport, this is the one step. Then we have transport or diffusion through the reduced iron oxide Fe3O4, and then the gas reaches at the interface, and where this particular chemical reaction takes place, which is also not operating at equilibrium, it is away from equilibrium. And I have mentioned that the interfacial concentration minus the equilibrium concentration is the driving force for this reaction to proceed. Now, for the first step, boundary layer mass transport, I wrote this expression that n dot CO is equal to 4 pi r0 square. Yesterday I think I wrote small r, and it is, I think, let us make the notation. So, this is what it is, the original diameter of the sphere. Okay? So, 4 pi 0 square multiplied by the mass transfer coefficient, and then we have the concentration difference, that is the CC0 bulk minus CC0 surface. Earlier, in all our assumptions of chemical reactions to be at equilibrium, the concentrations were, most of the surface concentrations were known. So, this is I have represented as C sub 0 bulk. So, this is say suffix S, and this is the carbon monoxide concentration at the surface. That is what is the notation here. So, this is this concentration, and this concentration we must know that it is not known to us. The bulk concentration, of course, is known to us. Then, considering the diffusion, we have also represented that n dot CO is going to be equal to 4 pi, and I represented it as d effective CO, because CO was assumed to be diffusing through the pores as well as through the bulk materials, and this is R0 into Ri, R0 minus Ri, and multiplied by the concentration difference, and that concentration difference now is CCO surface to CCO at interface. That is the driving force for diffusion. So, there is a difference between the concentration level of carbon monoxide here, and as a result of which the carbon monoxide is diffusing. And then I want to find out that this is for second step, or I think yesterday I said step 1 and step 2, and now we are to find out that what is NCO for step 3, which is going to be. So, that is where I left yesterday. These two have been readily obtained from our study of the mass transport fundamentals, because we have not studied in this course the chemical kinetics part. So, now we will calculate that how to calculate the flux or the net moles of carbon monoxide which is being generated, carbon dioxide which is being generated, or carbon monoxide which is being consumed because of the chemical reaction itself. Now, we know that the rate of reactions are given in terms of any reaction. If you take x going to y, for example, then we can say that the rate at which, so we can basically is a rate constant small k and then dx, and we can say x, if it is a first order reaction, then we can say that this is proportional to x. So, if x is in kg per meter cube or kg moles per meter cube, then k, the rate constant, will obviously 1 by second, and that will make the two sides identical. In this case, of course, we want to express, there is a forward reaction taking place and there is a backward reaction taking place, because they are competing in order to reach equilibrium. So, rate of the forward reaction, if I say that I want to calculate in terms of flux, in that case the flux of CO will be given in terms of the forward reaction rate constant multiplied by the concentration of carbon monoxide at the interface, where now this, because I want to express in terms of flux of carbon monoxide, so this is no more going to have the same dimension here. This is going to have a dimension, this is like a mass transfer coefficient meters per second. So, we have to manipulate in order to get the rate of reaction in terms of. So, this is the forward reaction. And similarly, we have the backward reaction. Okay? So, the flux of carbon monoxide and the backward reaction whereby, so this is going to be carbon monoxide is going to be, so we can say that forward reaction rate, I will not write it here in dot CO because it is going to be confusing. So, this is equal to my forward reaction rate, forward reaction flux, and that essentially implies, as I repeat again, that this is to be in length per unit time, so that this word flux is consistent with this expression. And similarly, we have K backward, okay, and we can say that this is equal to CCO2 at interface, and there, so the net rate, net flux, net, this is backward reaction actually, backward reaction flux. So, the net flux is going to be forward minus backward. So, Kf CCOI minus Kb CCO2, that is the net rate. And if this is the net flux, then I can multiply this net flux with the area, and that area is going to be 4 pi Ri square, because this essentially represents, here is the reaction which is taking place, and this radius is essentially R psi by L, which is changing as a function of time because of the nature of the problem, which being pseudo steady state diffusion. So, therefore, I can say if this is the net flux, then n dot CO due to reaction should be given in terms of 4 pi Ri square. There is a surface area, and then we have Kf CCOI minus Kb CCO2. Now, some mathematical juggling is going to be necessary in order to find out that what is the final form of this particular equation. Now, we must understand that there is one, we can say that C, the overall concentration, is going to be equal to CCO plus CCO2. That is going to be at the interface also, it is going to be valid. That is going to be when the reaction approaches equilibrium, if it attains equilibrium, then also this reaction equation is going to be valid. So, therefore, I can write here that this reaction, this term can be given in terms of 4 pi Ri square, okay, and then we can say Kf CCOI minus, or you can make, you can write it as Kb, okay, into CCO C minus CCO I. So, just by substituting this, we can do it. Okay. So, I have substituted instead of CCO2I as per whatever I have written here, okay, that CCOI is going to be, CCO2I is going to be C minus CCOI as per this equation. So, that substitution has been made here, okay. And now, we can bring this, we can say that look, this could be equal to, if I, from here, I again coming here. So, I want to take the forward reaction rate constant common. So, if I take this to be common, then this becomes is equal to C COI, okay, and this becomes equal to, and I can write it as plus CCOI minus C. I have just changed the sign, so I have made it plus, and then I can say that this is going to be is equal to Kb Kf by Kb, because I have taken Kf common, okay. So, I can write this expression. We also note that Kf by Kb is what? Kf, we have a definition at equilibrium constant, K forward by K backward, and that is in this particular case is going to be CCO2 equilibrium divided by CCO2 CCO equilibrium. If you write like this, how I have represented, so equilibrium concentration can be also be represented just in our style. So, this is the high school level definition, that the equilibrium constant is defined as the ratio of the forward to the backward rate reaction. Okay? Now, so we got up to here, and then if you see that this term can be further modified. So, I have two different terms. So, I have 4 pi r square Ri square, and then Kf, the forward rate reaction, and then we have CCOI. So, this is, I can now erase this and I can say that, look, this term is going to be now my K equilibrium, where capital K is the equilibrium. So, if you operate with CCOI, then I can get CCOI common, and then I get 1 plus 1 by K. And then I am left with what? Instead of, if I take this CCOI, then we have, okay, I have, I think, CCOI, that's what I have done, and then instead of C, we have here minus C by K. That's what we have. That's what comes out. This C again can be split into CCO2 equilibrium and CCO2 equilibrium as it is defined here. And also I know that I have written here, I think somewhere, yes, if I write down, if I replace this now C with equal to CCO2 equilibrium plus CCO equilibrium, CCO equilibrium, CCO equilibrium. So, that can be replaced, and again this CCO2 can be said to be is equal to K times CCO equilibrium. So, two-stage substitution I am going to do now. So, I have, up to this point I have derived. So, now the next step would be from here I will change this C and substitute CCO2 plus CCO, this expression instead of C. So, I get, instead of one term I will get two terms, and then everything here I can convert in terms of, when I substitute this CCO2 equilibrium in terms of the equilibrium constant and CCO2. So, a similar term is going to come here, and that term you can clearly see from here is going to be, the final expression is therefore going to be CCO equilibrium into 1 plus 1 by K. That is what is going to come out. So, if I do the substitution, first I replace capital C by CCO equilibrium plus CCO2 equilibrium, and then eliminate CCO2 equilibrium in terms of K and CCO equilibrium. In that case, I get this particular reaction, final expression, and then I can say that, look, from here my final expression becomes n dot CO, and this is the third actually. Now I can explicitly say, so this is n dot CO2, this is n dot CO1, 1 represents the boundary layer mass transfer, 2 represents the diffusion, and third represents the chemical. So, this is going to be 4 pi Ri square, which is a function of time, Kf into CCOI minus CCO equilibrium into 1 plus 1 by K. So, K is the equilibrium constant, and this K is the reaction rate constant in meters per second, and this is dimensionless, as you all know. Now, we have gotten, so now as you see here, from this equation, from this expression, we can write down that this is what it is. I am going to make my life simple. I will divide this by n dot CO1, and then I will say that this is going to be is equal to this inverse of Km. That is what is exactly the same equation. So, I would say that this is going to be, if I write down now, so this is going to be 1 divided by 4 pi r0 square into km. So, that is what it is I meant. So, equation 1 I have rearranged. I want to do it for this equation also. So, this is n dot COI. So, I can say that this is, if I divide it by and this side is going to be inverse of this particular parameter. Okay. So, I can say that this is going to be now so, therefore, I can do the same thing here, and then I can say that look, my C0, this is going to be from here, I will say that if we consider this, then from here I can write that CCOI excuse me. So, what you see here now, so I have structured them in a convenient style. We must understand here, yesterday also I have mentioned that this parameter NCOI will be equal to NCO2 is going to be equal to NCO3, because the same carbon monoxide which is crossing here, the flux, the same is diffusing here, there is no scope for any accumulation here, it is a steady state problem, and the same is being consumed in the reaction itself. So, they are numerically equal. So, we will now say that we can now remove this if they are numerically equal 1, 2 and 3, and we can represent. And if we now sum them up, we arrive at a, because 3 steps are working in series. So, I would say that if you sum them up, then what you are going to get, you can look at it, this. So, this and this is going to cancel out, this and this is going to cancel out. So, I am going to have on the left hand side now I write the main driving force from the bulk concentration to the interface concentration, the overall potential difference, okay, CCO bulk minus CCO interface divided by n dot CO. That is what is going to be, and this is going to be equal to now 1 divided by 4 pi r0 square km plus r0 minus Ri divided by 4 pi d effective into r0 Ri, and then this is going to be equal to 1 divided by the last expression here, that is 4 pi Ri square kf into 1 plus 1 by k. And therefore, I can now say yes, that is fine. So, if I take out this 1 divided by 4 pi r0 square common, then I get 1 divided by k sub m, this is r0 by Ri, and then we get 4 pi d effective Ri by R0, and here I get 1 divided by 4 pi. This is R0 Ri, so it has become Ri R0, 4 pi Ri by R0 squared into Kf times 1 plus 1. This is mass transfer coefficient, meters per second, inverse of that is the dimension. Similarly here, if you can look at it, Kf, the forward rate reaction, if you remember I said in the beginning that my rate constant is not going to be 1 by centimsecond, it is going to be length scale, it is like a mass transfer coefficient, K is dimensionless, Ri by R0 is dimensionless. So, Kf and Km has the same dimension. If you look at it here, okay, then you can see this is dimensionless, okay, this d effective is meters square per second, and this meter square per second will cancel with 1 meter, this becomes meter. So, they are all dimensionally consistent, and now if we represent this, we can say that 1 by 4 pi R0 square, and this term is going to be represented as 1 divided by K overall, which these are the resistances actually, as we will see. So, therefore, if we now manipulate with this equation, what do I get? I get the final expression, that is n dot CO is equal to, I take it like this, then 4 pi R0 square. So, 4 pi R0 square is the surface area, okay, overall mass transfer coefficient, or which is the inverse of which is the resistance multiplied by the overall mass transfer potential difference. That is the final expression. So, we have got 3 resistances here, and when you assume one single kinetic step is the rate limiting step, then what happens is this will cancel out if you assume boundary layer mass transfer. In that case, we will take that this is the bulk concentration and this is the equilibrium concentration now, because this step is no more existing, this is assumed to be diffusion is assumed to be fast. If when I assume boundary layer mass transfer is the rate limiting, this means diffusion is fast relative to boundary layer mass transfer, reaction is fast. So, therefore, this concentration prevails right up to this. So, the equilibrium concentration, the moment chemical reaction is the equilibrium, we have equilibrium concentration of the interface, and that equilibrium concentration will prevail here, and in that case what happens? We have the driving force will be CC0 bulk minus CC0 equilibrium, and in that case this term will cancel out, and this term will also cancel out, and then we will have the equation for overall resistance will be given in terms of only the boundary layer mass transfer theory, okay, and that is what we have all the time start. So, you can now add 2 other steps also, removal of the product, diffusion of the product, and diffusion of the or transport of the product through the boundary layer, and then you can not only have 3 terms, 3 components of the overall resistance, but you can have the 4th component and the 5th component following exactly the same thing. So, the diffusion treatment is analogous to the carbon dioxide diffusion, okay. Similarly, boundary layer transport is. So, equivalent to these 2 steps, you will have 4th term and the 5th term. So, nothing new needs to be done really, you have to just collate the expressions together, manipulate it a little bit, and then cast it in terms of the overall mass transfer resistance to the whole process. So, we will stop here in terms of the solid liquid mass transfer is concerned, and this is a typical case where we have shown that when more than one step could be rate limiting, then also it is possible to provide a rate expression. And then of course, you can find out that at what rate, because it is a case of equivalent counter current diffusion. So, you can find out that how much of carbon monoxide is being consumed and how much of carbon dioxide is being generated, and one should be able to find out that of course, this will necessitate that you know all these parameters, the rate constant of the reaction, the equilibrium constant, okay, these are to be known and at that particular instant Ri also has to be known. So, if you stop the reaction at a certain moment, take out this entire spherical thing from the chamber and freeze it, let the reaction stop, then cut the sample and look at it at the microscope, you will be able to find out that what is the Ri, okay, and then you will be able to know that how much of material has reduced, what should be the volume of carbon monoxide which has been generated. So, one can not only carry out this reaction, this exercise, but one can also compare with the rate of reduction by looking at that what is the position of the interface and then comparing it with this particular reaction model, which we call as a topochemical reaction model, because all the interfaces, the reaction interfaces has been assumed to be parallel to the original interface, and that is why it is a topochemical reaction model where 3 steps are considered to be controlling the rate of the process. We will go to the last topic now, and then that will be the formal ending of the course, and this is I just want to talk about 2 fluid mass transfer. There are many examples of 2 fluid mass transfer taking place. Okay. Mass transfer between 2 fluids application. These 2 fluids could be liquid-liquid, 2 liquids, immiscible liquids like slag and metal, or this could be a gas and a liquid. So these are the 2 possibilities. One is gas and liquid. So I will discuss both of this very briefly, and number 2 is liquid-liquid mass transfer. Let us briefly look at a process of gas-liquid mass transfer. One example which you have done is, and you know already, is vacuum degassing process, for example. In VD process, what happens when a container containing molten metal is kept inside a vacuum chamber, then what happens is that we have dissolved gases like nitrogen, hydrogen, etc. They escape from the metal to the gas phase, because you have a very low pressure here, that could be 1 millibar or even less than a fractional millibar pressure in the container. So this is an evacuated chamber, and here what happens is that if you have nitrogen dissolved in the metal, that nitrogen becomes nitrogen gas and it is sucked out. So this is basically the process that what takes place in the vacuum degassing process. This is called a tank degassing process. Now, in this removal of gases through tank degassing is a very common practice in the industry. In all high sophisticated application of materials, particularly metallic materials, metals containing dissolved gases are routinely subjected to vacuum chambers, and as a result of which what happens, this reaction is facilitated from left to right, provided the partial pressure of nitrogen in the gas phase is small, and this thermodynamic conditions is satisfied by simply subjecting the container containing the molten metal in a, so this is liquid metal, and liquid metal contains dissolved nitrogen and hydrogen, and that is the reaction that takes place. What does the reaction takes place? The reaction does not take place here, reaction does not take place here, reaction takes place at the interface. Okay. So this is a interfaces, this is the ambient, which is the gas phase, pressure may be very low, and this is the liquid. So the reaction takes place basically at gas and liquid atmosphere. Okay. And in this case what happens is that we have, for example, how does that process occurs? Nitrogen or hydrogen which is dissolved, it moves to the interface. The first is transport to the interface. So they are all available here. So they are readily available initially at the time, everywhere nitrogen or hydrogen is in the dissolved state. But once nitrogen from here starts to leave, there is a concentration gradient here. So all the nitrogens are going to be removed. So this nitrogen and hydrogen from the lower part has to be taken to the interface, and then only this reaction can really take place. So therefore, in all cases of degassing operations, you will see there is some kind of a stirring which is present in the system. That stirring takes the dissolved species from the bulk continuously to the interface, and where this particular reaction takes place. Typically, the dissolution reaction or the dissolution or the degassing process is assumed to be melt phase mass transport control. Melt phase transport control. That is assumed to be the rate limiting step. So, one single kinetic step. So, I would say transport of nitrogen from the bulk of the liquid to the interface. This is the first step. Once nitrogen reaches here, the second step is the chemical reaction, and that chemical reaction is assumed to be at equilibrium. So, the degassing process is characterized in terms of the melt phase transport control process. And then we assume that there is some kind of a boundary layer here through which. So, therefore, the concentration here is less and the concentration here will go something like this. This is the concentration profile basically. Okay? So, if I draw a line like this and then draw a line like this. So, this is the concentration of nitrogen, this is 0 and this is some C bulk concentration, and this is as a function of distance, and there is a boundary layer here. So, the transport from here to here is not so important, it is the melt transport across the boundary layer, and we know. So, therefore, from the theory of boundary layer mass transfer, we can say that the rate at which the flux of nitrogen, I would say, or the net rate of transport of nitrogen will be given in terms of a mass transfer coefficient Kn into interfacial area, and that interfacial area is the ambient liquid interfacial area. That is what A is. And then, because this is we have a bulk concentration and this reaction is equilibrium, and that the partial pressure here is small. So, whatever nitrogen reaches at this interface, that nitrogen is immediately converted into the gaseous phase, and that in the gas phase the nitrogen concentration is extremely small because it is under vacuum. So, this could be, note that this bulk concentration is a function of time, because as nitrogen is continuously removing, this is also changing. And so, therefore, we can say that look, a mass balance equation. So, this is concentration, this is area, and this is the mass transfer coefficient of nitrogen, and this is giving in terms of, I would say, the concentration of nitrogen in terms of Kn by, or we can write C sub B, the bulk concentration, and this is rate at which the bulk concentration of nitrogen Cbn, that is what it is, and this is decreasing. So, therefore, there is a negative sign here, where V represents the volume. This equation we have seen already, I have derived this equation. Okay? So, the only problem here is that we should be able to calculate this first order solve this first order kinetic equation at T is equal to 0, C bulk nitrogen is equal to C bulk nitrogen, the initial nitrogen content in the system. So, we require the mass transfer coefficient, okay? And that mass transfer coefficient, as I have told you, can be obtained from either the low eddy theory, small eddy theory, or the large eddy theory. So, you can have the mass transfer coefficient calculated Km. So, this I will say that this is mass transfer coefficient of nitrogen, Kmn of nitrogen, that will be given in terms of 0.4, and because it is a surface renewal theory, so we will see that it is d to the power half, and then if we have small eddy theory, this expression I have written, we will use this expression, or Km comma n. For large eddy, we will, where u is characteristic length raised to the power 0.5. These expressions I have given. L is the characteristic length, D is the diffusion coefficient, and I have also mentioned that characteristics of the two fluid mass transfer is that the diffusion mass transfer coefficient will be proportional to square root of D. That has been reflected in this particular case. In this case, what happens? Because of the application of the vacuum, as well as that I said that we will have some kind of a stirring, and that stirring of the metal is by inert gas purging. Some kind of a gas which is say argon. Argon is introduced. The argon bubbles actually rise through the liquid, and this causes good amount of stirring. So as a result of which, this interfacial area that I have represented here, A is not equal to pi r0 square, in which r0 represents the vessel radius. Indeed, the interfacial area through which the mass transfer takes place, the gas, could be significantly larger than the pi r square because of the deformation of the surface. Okay? Because bubbling is taking place, there are droplets which are being ejected onto the surface, that droplets come back. Okay? So as a result of which, enormous amount of surface area could be created, and if you try to do this calculation, even if you can calculate the mass transfer coefficient, okay, the interfacial area calculation in this particular case, it is only when you can say that there is no agitation overall, you can perhaps work with pi r0 square, but in most of the industrial processes, since there is going to be extensive amount of agitation, there is going to be continuous gases evolving from the liquid surface. So as a result of the application of the vacuum, also there is going to be significant distortion of the interface, which will make this area actually A significantly larger than the planar interfacial area, could be 10 times, could be 20 times larger. So this brings in some kind of an uncertainty. So even though the solution is very easy here, the estimation of interfacial area becomes a very big problem for two fluid mass transfer cases. Okay? And for that, many a times advanced computational procedures are applied, okay, in order to find out that, there's the gas liquid phases are there, and one can do a multi-phase modeling in order to find out that how does the interfacial area, develops in the system through advanced computational calculation procedures and so on and so forth. So if you want to do a two fluid mass transfer calculations, there is very rarely you will be able to do it by analytical means, because of the simple fact that the mass transfer coefficient calculation, as well as, for example, you need, if you want to apply the large eddy model of mass transfer, you require a velocity scale u, and that velocity scale is not known here. So in order to know the velocity scale, in order to know the interfacial area, you have to do additional exercises. You have to do calculations, and those calculations are very difficult calculations, complex calculations. They're basically multi-phase turbulent flow calculation procedures that needs to be applied. And then, but if somebody says that I want a limiting value to get an idea, one can of course take a value which is equal to 10 times the pi r0 square roughly. Okay? We know it could be 10, it could be 20, we really don't know, but for the sake of solving a problem, if I can give you this, and then I can say that this energy, you apply a lower eddy theory, and then this you consider to be the energy which is dissipated because of the motion, mass transfer is equal to some parameter. This is the input energy into the system which causes the stirring, and this is the efficiency of conversion of input energy into the turbulence phenomena. In that case, the energy dissipation can be calculated, because this can be calculated very easily, what is the energy input, and if this fraction is known, so we can say 30% of the input energy is equal to epsilon, this is kinematic viscosity, this is diffusion coefficient, so a mass transfer coefficient can be calculated. So some limiting simple calculations can be performed in this particular cases. Another example of this is the dissolution, for example, of nitrogen in tundish, steelmaking tundish. So we have from a ladle through a shroud, molten metal comes into tundish, and then at steady state the molten metal goes out. So this is tundish, this is shroud, and this is ladle, and there is continuous casting mold. Because this joint is never perfect, and that there is a huge head difference, so air gets sucked into the molten steel itself. So the molten metal comes from shroud. We want to protect molten steel, and that's why we have used a shroud. Open air timming is never done, because steel present in the ladle will otherwise get oxidized. Steel ladle is covered here, so is tundish, which is also covered here. Okay, and this is the interface. The interface is going to be represented like this. So we have air which gets sucked into this, and as a result of which what happens? Nitrogen and oxygen gets dissolved into molten steel. So you have some initial nitrogen here, and you will find if nitrogen, because there is no source of nitrogen, if nitrogen out is greater than nitrogen initial, that means the molten metal has been exposed to atmosphere. That means some amount of, here there is no scope because it is covered with slag or tundish powder. So it is through this shroud ladle joint that nitrogen or air has got in, and as a result of which what happens, you have gotten output nitrogen, dissolved nitrogen, which is greater than the dissolved nitrogen which is initially present in the, so these are all. And if you do a material balance, the material balance equation looks like this is the volumetric flow rate of the liquid, this is the nitrogen which is in the concentration of nitrogen. This is meters cube per second, this is concentration of nitrogen kg per meter cube, so this becomes kg per second, and then this is the output nitrogen, and that is equal to input nitrogen plus the nitrogen which gets dissolved into steel because of the entrainment. So whatever nitrogen comes here, a part is going to be escaping, gas nitrogen is going to be escaping. So this is, we are talking about a balance on dissolved nitrogen balance. This balance is not on gaseous nitrogen, balance on dissolved nitrogen. And here what happens is, from gas bubble, nitrogen is going to go into the liquid. So that's how the dissolution takes place. So the interfacial concentration, again we will assume that melt phase transport is the rate limiting step. This is the bubble, and this is my liquid. So there is a, we know now we can go move rapidly. So there is a reaction at the gas liquid interface, and that reaction is the reverse of that reaction, that nitrogen gets into dissolved nitrogen. That takes place. And this reaction per se is taken to be at equilibrium. So therefore, the surface concentration is known to us. It is again assumed to be melt phase transport. So there is a boundary layer through which it is transport. So the same equation is applicable in this particular case. So therefore, this R dot term can be represented as R dot is equal to, so these are all kg per second, this is also kg per second or kg moles per second. So this is the mass transfer coefficient of nitrogen dissolution multiplied by the area, and then we have the concentration difference, and that concentration difference is the bubble surface concentration difference of nitrogen, which is known from the equilibrium, minus the initial nitrogen content. But this concentration is significantly larger. Nitrogen could be here about 20 ppm, 30 ppm. On the other hand, this surface concentration or the saturation concentration could be about 180 or 340 ppm in some steel, or 300 to 400 ppm in some steel. So this term is negligible in comparison to the first term. So we come to the same problem again, that what is the mass transfer coefficient, what is the interfacial area, and in this case it is far more complex than this, because the gases which are entrained here are going to form a large number of bubbles here, which will have different shapes, different sizes, okay, and estimating for the number of bubbles as well as their shape and the total number of interfacial area is a horrendously complex task here. So the same issue is also anticipated in this particular case. Here also in this particular, these are the problems, challenging problems in metallurgy which people are trying to solve now, because we require enormous computational power in order to simulate this problem on an industrial scale, and thereby find out that what should be the gas liquid interfacial area, so that we should be able to find out that what is the net rate of reaction, and then by measuring this concentration of nitrogen we will be able to predict that what is the output concentration, and so on and so forth. And we want to limit, and in this particular case we must understand this area is a very important factor, okay, and larger is the area, larger is the rate of transport, because this you cannot control. This is a fixed parameter given the temperature, this is the equilibrium value. It is only the mass transfer coefficient as well as the area that you can control in the whole thing, okay. The mass transfer coefficient can be controlled if you can dampen the velocity because this is a function of velocity. Similarly, if you can eliminate nitrogen pickup or limit nitrogen pickup, then the number of bubbles or the number of total interfacial area formed could be less. So it is these two parameters which needs to be controlled in order to control the rate of dissolution of nitrogen or oxygen. Similar arguments can be advocated with oxygen, but oxygen is far more reactive. So an additional term, reaction of oxygen, depletion of oxygen will come with a negative sign because oxygen getting in may react with aluminum. Nitrogen, we have not assumed dissolved nitrogen does not react with anything. Whatever comes here, okay, goes out is equal to whatever is coming in plus whatever is being generated here. So nothing is lost here. But if you do the similar balance equation for oxygen, we'll find that an additional term needs to be incorporated, which will take into account the consumption of oxygen because of reaction with silicon, dissolved silicon or dissolved aluminum, and so on and so forth. But the point that I'm trying to make here is that when you try to address two fluid mass transfer problems, they are far more complex than the gas solid mass transfer situation, and that complexity basically originates because of the unknown parameter which we call as the two fluid interfacial area. And the two fluid interfacial area, depending on the processes, could be dramatically different. Okay? Here we have one kind of an area, in the other case we have, Now, for example, in this particular case, the same problem, if you consider a slag metal reaction, for example, for a moment you assume, I want to discuss now two fluid mass transfer. So gas liquid mass transfer I have already said. Given you two examples, one is vacuum degassing, the second is transport from or the transfer from ladle to tun dish. So the nitrogen is ingressed or entrained into molten steel. So it's a gas liquid mass transfer through bubbles in liquid, and here what happens is the dissolved nitrogen gets transferred into the gas phase itself. So it is the melt in ambient interfacial area, that's what we are talking about, and it's the melt bubble interfacial area that we are talking about. And these two problems are similar in nature, where the uncertainty gets in to the calculation because of, as I have repeatedly said, this particular parameter which represents the interfacial area between the two phases under consideration. Now, in the same problem, if you are considering, for example, suppose there is now no air ingression is there, but the slag often contains, for example, silica. And what happens, metal also contain dissolved aluminum. Where from dissolved aluminum comes in steel? Dissolved aluminum comes from the deoxidation of steel that you have all studied in your undergraduate. And this tun dish flux, why do you require a slag here? Because we don't want heat to be lost. So we have put a physical cover over the tun dish, we have put some slag layer. This slag layer also helps in absorbing those tiny little inclusions which are floating from the surface. So they absorb those inclusions, their removal. But in the process, what happens? The two liquids come in contact at the interface. Okay? This is the interface, slag metal interface, and at slag metal interface, often a reaction of the type is possible. One can balance this equation. So the dissolved aluminum will react with silica, and then silicon will get into the metal, and aluminum after oxidation will get into the slag. And in this particular case, as you can see here, that we have transport of aluminum from bulk to the interface, transport of silica from slag to the interface. Once they come, then they can see each other. That's how the chemical reaction takes place. That is the third step. And once the reaction takes place, then the product silicon gets into the metal and Al2O3 gets into the slag. This reaction takes place at the slag metal interface. It is not possible here. It is not possible here. It is possible only at the slag metal interface, the reaction. Okay? Now, there are 5 kinetic steps: transport of aluminum, transport of silica, chemical reaction, transport of silicon back to metal, transport of aluminum. There are 5 kinetic steps. And if I assume that only one single kinetic step is rate limiting, and in that case if you assume that the transport of silica from the slag to the metal interface is rate limiting, that determines, in that case you should be able to find out again that at what rate silicon is coming in, and from this reaction you will be able to find out that at what rate aluminum is decreasing from the system. So with this reaction proceeding, okay, taking place, what is happening? Gradually the aluminum, dissolved aluminum is going to go down and down and down, which we call as an aluminum fading phenomena, and the silicon content of the metal will go increase and increase and increase. So if you can find out that how much of silica, because there is a molar ratio here, if I balance this equation, so I can say that it is, I think, 3Al, if I do it, so silicon SiO2, so we can say 2Al2O3, so then I can say 4 aluminum, okay, and then 6 oxygen, so you can say it is 3 and then it is 3. This is the balanced equation. So if we know that for every 3 moles of silica, 4 moles of aluminum depletion is going to take place from the bulk itself. So if I can calculate the flux of silica, I should be able to calculate the rate at which aluminum is depleting. So in this case, the flux of silica in SiO2 can be calculated under steady state condition when nothing is changing as a mass transfer coefficient, okay, times the interfacial area times the bulk concentration of silicon minus the interfacial concentration of silica. Whatever silica reaches at the interface, it is immediately consumed, because this reaction is assumed to be very, very fast. So the interfacial concentration of silicon is going to be equal to 0. In such cases, because the Tunn dish is, when you do not have much gas entrained, so the Tunn dish, this interface is virtually quiescent, very stagnant, nearly stagnant. So this interface in this particular case can be taken to be the planar interfacial area, and then by calculating the mass transfer coefficient on the basis of those two models, one of the two models, one should be able to calculate that what is the flux of silica, and based on that one should be able to find out that how much of aluminum really, by multiplying. So if you want to find out for corresponding aluminum, because it is 1.33, so you will multiply this NSiO2 by 1.33 and you will get the rate, how many moles, or what is the mass of aluminum which has really got decreased from the system. So in this case, the calculation of the interfacial area is relatively simple. So interfacial area calculation will depend on the specific nature of the problem itself. This is very simple. On the other hand, the vacuum degassing problem as well as the gas entrainment through the shroud, they are not so complicated, and they may warrant more elaborate calculations through a multi-phase model itself. So I think I have given enough food for thought, and this finishes the entire syllabus of the course that I was planned to teach through about 28 lectures. So I have taken one more lecture, that's 29 lectures, and then we will have about 11 problem solving sessions, and that 29 plus 11 will make it a 40 lecture course. And I think the entire discussion starting from day 1 to today's lecture should give you a good overview of the relevance of the subject in terms of its industrial application, and particularly in terms of metals and materials processing. Okay, thank you.